Okay, so here we want to talk about our presentation that is called Point Cloud Based Indoor Navigation Prototype using Visual SLAM, Mapping, and Relocalization. So here's the table of content that we want to presenting. First, we talk about motivation, like the challenges and the solution, and the innovation that we bring into this research. And the second is principles. There's the technique and method we use to realize this research. And the third one is final result. This final result we will see about video and some result that we have done in this research. The fourth one will be conclusion. It will be an overall summary of our research, and the last will be futures work. It's an enhancement and future application of our research. Okay, first, let's talk about our motivation why we want to bring this research. First, the challenge. Global Navigation Satellite System or GNSS signals such as GPS are highly effective for outdoor navigation. However, these signals face significant challenge when navigating inside building due to signal attenuation and blockage by wall and ceilings. So here's what our solution for solving that challenge. So we want to implement an affordable indoor navigation prototype that operates without GNSS. So our system will use ORB SLAM tree, which creating a detailed 3D key points map from a building's interior. During navigation, the system captures camera frames and matches them against this pre-built map to determine the user's precise location in real time. And this innovation is talked about by leveraging visual features instead of satellite signals. Our approach enables accurate indoor positioning where GNSS files, opening possibilities for indoor navigation, robotics, and augmented reality application. And let's talk about the principles we use in this research. So the figures 2 shows the flowchart system with two major modules, which the first one is mapping module, which is the green box in the figure 2, where we will have an input about video recording of the building interior, and of the video recording itself will be processing with the RB tree, which will analyze frames into extract 3D key points. After that, we will have an output about map file, which is file.osa, and some vocabulary database. It's called Big of Word or BOW. And then this is the main part. Which talk about localization module, which is blue box in figure 2. At this module, we will have an input about live camera stream from user's device, and from this live input camera, we will processing for each frames to extract the features, and then we will find the candidates, and after we found the matching candidates, the matching keyframe candidates, we will solve the pose, which is the position and the orientation, and after we found it, we will calculating the confidence score, and after that we will output the pose of the higher confidence scores, which is the expectation of this model will be user's 2D position, which is X and Y coordinates with its orientation. And the figure 3 and figure 4, which we representing about each process. Like first, the figure 3 will be showing the mapping model, and the figure 4 will be localization model. Okay, here's the one. First, let's talk about the mapping model. We use the RB SLAM tree as a state-of-the-art visual SLAM algorithm to construct a 3D points cloud map. And how does the mapping model works? For first, the camera movement. The camera will be walked through the building recording video, and after it, the video will be extract the features, and RB SLAM tree detects the ARB features in each frame, and the map. And after we creating the map building, it will be containing the keyframes and 3D points stored in the map. So the output will be the 3D key points map, which is the OSI file, and the vocabulary database for fast matching, which is backward. And you can see the camera trajectory showing the recording path as shown in this video right next to this slide. You see. Okay, then let's continue. This is the our main program, which is the finding location or localization module. So the first step is will be extracting ORB features and find the candidate keyframes for each raw camera frame. So when the new frames arrive here, so we will extract the ORB features and compare them against our vocabulary database using backwards like this, and identify the 5 most similar keyframes from the pre-built map. And BOW converts image features into a visual vocabulary for fast similarities comparison. The top 5 keyframes chosen as the reason of the balance. At this process, we will expecting about there is a 5 candidate keyframe that chosen as the candidate match keyframe. Oh, sorry. Okay, then the second step will be matching the features between camera frame and candidate frames. So we will perform the features matching using OpenCV's program called brute force matcher and lowest ratios test, and give us the 2D points of the query image and their corresponding 3D points in the map. So after we found the corresponding frame here, so it will for each key point it will do a brute force for each key points in the map. So after we do all of this matching with brute force, and after we found some sort of score, we do a lowest ratio test. If the ratio lower than 0.75, then it will be chosen as the match key points here. So you see the key points here will be matched into one key point in the map, and for each match key point will be a store of the UV pixel coordinate here, UV, and the XYZ in the coordinate in the map. And the third step will be solving camera using point and perspective ransack, which we call the PNP ransack here. So given the 2D and 3D corresponds like this, we have the 2D key points and 3D key points in the map. So we use PNP with ransack to compute the camera rotation and translation here. We will expecting an output about R metric and T metrics from the PNP. And after we process PNP, we will get the R and R also T metric. Then we can compute the camera position by formula minus transpose matrix of R times to T, like this. Okay, so the output will be where's our camera in XY position based on this 2D key points we have stored and 3D key points stored we have in the map. And for this each match key point, we will see one inlier here, which is have a same side here from the C0 point of view. And the last step will be ranking the candidate and select the best match. The system then calculate the confidence score by the formula 2 based on the inlier ratio from PNP calculation and BOW score. So which constant K1 is 100 and K2 is 1000. So after we do some calculation, in example, after we have a 5 key points candidate keyframe here, so each of candidate will be calculating the score itself. Like in example, the keyframe 1 will have score about 79, and the keyframe 2 will have 95, and the rest like this. But in our case, we will output the position if the confidence score is higher than the threshold, which is 60, and pick the highest among all of the candidates. Like in this case, we will pick keyframe 1 because the score is above 60 and is the highest among all candidates. So the keyframe 1 will have the pose from the PNP and solving a position camera which has a value xy, then this xy will be our position. Okay, so you can see by this video, you can see our performance and demonstration. So I will zoom out first. You will see here. So in this video, you will see our real-time navigation based on the matching key points between this camera frame and this map, predefined map. Okay. So in this result, you can see as the user walks through the corridor, the system continuously processes frames and computes its position and orientation. And this robustness, we have some robustness in our program, like handles partial occlusion and recovers from tracking loss. And the best thing is like it works with the handheld camera motion, so it's not really have to smooth camera to have run this program. And you see after it's going turn back again, the orientation of our here will turn back here facing this direction. Okay, we also have a different scenario, which is here. We run a different video to see is it do we have a robust results like this. You see if the video is just moving, turning 360 degree, it will be has a some likely accurate position and accurate orientation like this. So, and as the conclusion in this work, we have created a relocalization program that can find our location inside of a building. And to realize this work, we need to make a map inside of building using ORB SLAM3 with mapping module. When the localization module receives the camera's frame, which extract its features and matching it with the keyframes feature at the map using BOW to find candidate keyframe. Then for each corresponding candidate keyframe, we'll compute the P and P and solve the position of their keyframe. Finally, we calculate each of their score and choose the keyframe with the highest confidence score. The position of the highest score keyframe will come out as the result. And this technology, we believe, that empowers human and robotic application with reliable indoor localization capabilities. So for the future's work, we have some idea that we want to enhancing the scalability. So the current one, the prototype maps only have a single corridor, which is only around 15 meters. And our goal, we want to extend it to have a multiple floors with like around area around 500 meters with the multiple rooms. And the challenge of this improvement will be like memory management, map merging, and large scale loop closures. And to approaching this kind of enhancement, we need to implement hierarchical map representation and submapping technique. And the second innovation we want to do in the future for maybe the real-time navigation with AR visualization. So in here, the current one only provide the position coordinates, but we can enhance more, like add destination and selection based on path planning, and the user will be like have a overlay directional arrow on the live camera feed using AR. So in example, if the path planning will be has a result of a turn left in 5 meters, so there's a visual arrow that we should follow the arrow, and that's turn left in 5 meters. And this requirement of this technique will be we will need some integration with path planning and AR rendering. Okay, so here's some reference, which is you can see from what source we have taken from some source. Okay, maybe just thank you.